Designing the Oscar 2 for the state of Idaho. We're going to be referring to information that's found on our current design manual, which is going to be found on our products page in the state of Idaho. The Oscar has three main components. First one is the septic tank, which we refer to as a treatment vessel. We're also going to have a 1,000-gallon discharge tank, reverse flush headworks, and the Oscar component itself. It's comprised of a couple of coils with a basal area of medium sand. The Oscar is an acronym that stands for On-Site Sand Coil Area Recharge, and it describes what it is and kind of what it does. The Oscar is a proprietary treatment technology. It does produce a high quality of effluent from septic tank effluent to a BOD of 2 and a total suspended solids of 2 milligrams per liter, and it also acts as a final dispersal component at the same time. The Oscar has two main components, the coils themselves. We actually have two versions of coils. One is a 50 gallon a day, and then another is a 100 gallon a day design flow, and they're labeled an OS 50 and an OS 100 respectively. The other main component for the Oscar is medium sand, and we're looking at a minimum of a 12-inch depth of medium sand under the coils. Our OS 50 coil, or 5-foot diameter coil, is depicted here, and when it's assembled in the field, it'll have this same geometric shape. The OS 100 coil is going to be similar, but we have twice as much tubing, and it's going to be attached again to a white PVC bracket, and the overall footprint is 85 inches per coil. To compare the two coils, the OS 50, again, it's a 50 gallon a day design flow. It covers about a 5 by 5 area, or 25 square feet. We have 50 emitters, giving us 2 emitters per square foot. The OS 100 is just double the design flow. Its area is also doubled to 50 square feet, and we have double the emitters, but we have the same concentration of 2 emitters per square feet. Looking at the side view of an Oscar on a flat site, you can see we have the prepared ground surface. We'll have 12 inches of medium sand underneath the coil, and the coil needs to be installed level. And then we'll have a minimum of 6 inches of sand over the top of the coil. Now the remainder of the basal area only needs to have a 6-inch deep bed of sand. And so that will then encompass the remaining of the basal area. Now when we're looking at the comparison between the OS 100 and OS 50, we have to have the same amount of basal area available. But how we go about calculating or designing that geometric shape is going to be different. The OS 50, if we're looking at a 300 gallon design flow, is going to have a minimum length of 35.5 feet, as opposed to the OS 100 coils for the same design flow. We're only going to have a little over 23 feet. Now, the width to the basal area will be extended with the OS 100s, but depending upon the limitation of the site, it may be advantageous to go with the larger coil. And just to give you a visual look at what the two different arrangements would look like, the OS 100s are going to be more of a square geometric shape. The OS 50 are going to be more a long rectangular shape. But both of these have the identical square footage for infiltrative area, and they have the same amount of treatment capacity of 300 gallons a day. And on a sloping site, you'll notice that we've shifted the coils to the upper edge of the basal area. And again, we're maintaining the coils level, so we'll go through a design example to show you how we calculate what additional sand you'll need here depending upon the slope. And then the toe is going to extend out, and again this toe only has to have a minimum of 6 inches of sand on the surface of the basal area. Our tanks, we need two, minimum of 1,000 gallon for our septic tank, single compartment. And then we're going to have 1,000 gallon double compartment, excuse me, another 1,000 gallon discharge tank, single compartment. The treatment level coming into the system when we tested through NSF, our monthly averages were at about 220 to 240 milligrams per liter BOD NTSS. Coming out of the Oscar, we averaged 2 across the board. Now, getting into some of the particulars of the design, there really aren't a whole lot of aspects that we need to calculate for, but be aware that what we're doing is we're putting together a standard package so that we reduce the amount of design parameters that we do have to design for. For the most part, we're going to be using the same pump, same float, same pump tank for majority, say 85-95% of our design applications. But we will have to design the basal area given the soil type. We're also going to have to look at the hydraulic layout again according to the design flow. But we're going to be looking at the total dynamic head for the Oscar supply line. That we can't determine beforehand, so we need to give some parameters of how we address that. And then the tankage, actually is pretty straightforward, but we still need to compensate for any larger design flows if that's the case. Now our standard packages all have the same components. We're going to use the same control panel, same headworks, and this basically filters the material before it goes to the Oscar coils. We use as a given the same pump over and over again. We use an AY McDonald's, a half horse motor, 110 volt, 30 gallon a minute turbine pump. And we have some miscellaneous parts, floats, blank tubing, float brackets. There's also some transitional fittings to go from the tubing to the PVC supply lines as well that we've included. Now the standard coil arrangements that we have are going to be consistent irregardless of the soil type. So for instance, I'm using the example of an Oscar 300 gallon a day using the 5-foot diameter coils. And it doesn't matter if we're talking about A1 soils, a real coarse sandy soil, or if we're talking about a very tight loam, silt loam type soil in a C2. The amount of coils is going to stay the same. What will change is the basal area. So here we're going to go through two design examples. We're going to use a 3-bedroom design flow of 250 gallons a day. In our fictitious site, we're going to say that we've got 15 inches of soil over a restrictive layer. And we're going to look at a flat site, and then we're going to look at a sloping site. And I'm going to use 20% as the side slope that we're going to be designing for. And what we're going to be looking at is this same basic coil layout, both for the sloping and the flat site. And we're going to have to come up with the same basal square footage, but we're going to have different dimensions for the width as well as for the overall basal length. Again, there's going to be 4 criteria we need to look at. The minimum basal area required by code. We're also going to look at what I'm referring to as the minimum shoulder length. In our tables, we give this, and it compensates for the coils, the separation between each coil, as well as the additional shoulder setbacks, what I'm referring to. And then we're also going to look at the side slopes. Because we're installing the system primarily above ground or at grade, we're going to have a pile of sand. We need to compensate for the fact that we're going to have a side slope, and that's part of the basal area as well. And then, of course, we'll calculate the width. So looking at the basal area for a flat site, basal area is going to be the design flow, and what we're requiring is we're just for the basal area and the layout for the coils, we want to multiply our design flow by 150%. And then we're going to divide that factor by the loading rate. And because we're getting such high treatment quality, the state is going to allow us to use the secondary biological treatment system hydraulic loading rates. So they're a little bit higher than for the normal septic tank effluent. Again, 3 bedrooms at 250, soil type, and we're going to assume that we're in B2. So our design flow of 250 gallons times 150%, we're going to use 375 gallon a day design flow. To get our square footage, divide that design flow by 0.6, our application rate to the B2 soils, and we end up with 625 square foot. Now this is our minimum square footage, not our maximum. Next, we need to refer to the shoulder lengths. And we have these listed in design flows. For the most part, every 50 gallon a day increments. Sometimes we jump 100. But if we look at this chart, we don't have one for 375, so we'll have to round up to the next highest value. So for a 400 gallon a day design flow, we have a minimum shoulder length in feet of 44.5 feet. So going back to our illustration, that length that we're referring to is going to be from this end of the coil all the way to the other end with a 6-inch, what I call shoulder setback. So that overall length is 44.5 feet. And if you'll notice here, we've got 8 50 gallon a day coils for our 400, or in this case 375 gallon a day design flow. So we're missing one factor or component, and that is going to be this additional space here for our side slopes. We're going to have one on each end. So looking at a cross section of the Oscar, here's our coil, and this is our 6-inch shoulder setback. And because we're 12 inches tall and we're using a 1-to-1 slope, that means our side slope has to be a minimum of 12 inches. And we're going to have this same side slope on either end. So we have to take that 12 inches and multiply it by 2. So 12 times 2 is 24 inches, or 2 feet. So we're going to add our side slope of 2 feet to our minimum shoulder length of 44.5 to come up with a minimum basal length of 46.5 feet. Now to calculate the width, it's just as simple as taking our square footage, dividing it by our minimum length of 46.5, and we end up with a little over 13. I'm going to round up to 13.5 feet. So now we've done the complete calculations for this Oscar, in that we need 46.5 foot long by 13.5 foot wide basal area. We know that we're going to need the 8 coil arrangement. And by the way, this drawing is specific on how the plumbing is done, so we don't have to do any calculations there. And we know what the design flow is going to be based upon the fact that these coils are already prearranged and pre-calculated. Now, just to kind of review real quickly all the steps that we've taken here. Again, we're going to take our design flow of 250, multiply it by our design factor of 1.5, our design loading rate of, or design flow of 375. Again, our B2 soils of 0.6. So we make those calculations, the 375 divided by 0.6, we get to 625, and so forth. So anyway, I just have this written down in a different format for your review. So overall, when we're done with the design, we'll use these 2 cut sheets. They're actually on one sheet. We'll use a OS 400 5, indicating it's an Oscar coils, 400 gallons a day, using the 5-foot coils on a flat site. And our basal, again, is 13.5 by 46 feet long. And cross-sectional wise, this is what we'll be wanting to have installed by the contractors. Now, on a sloping site, everything is pretty much the same, except we have to compensate for 2 things, or make 2 changes. One is, you'll notice we've shifted this coil up to the upper slope of the basal area. What we're wanting to do is to take advantage of the fact that as water moves laterally down slope, we want to take advantage of the infiltrative area. If we left these coils in the center, we would lose infiltrative area on the upslope side. So that's number one. Number two is we want to keep these coils level. So what we need to do is compensate for the amount of sand on the downslope side. And it's a very simple formula. If we take the diameter of our coil, which is a 5-foot coil or 60 inches, multiply that, in this case of 20%, that's our slope of the site, that will mean we need an additional 12 inches of sand. So we're going to end up having a total of 24 inches of sand underneath this downslope coil and a minimum of 12 under the upslope side of the coil. Now what that's going to change is going to be our side slopes. If you remember in the previous illustration where we only had a 12-inch rise or depth of sand under the coil, we only had to have a 12-inch side slope. Well, here we're going to have 24 inches under the downslope side, so we're going to have 2 feet of a side slope. So we're going to use the exact same calculations. We've come up with the 625 based upon our design flow and the loading rate. We're going to have the same minimum soil or coil length or shoulder length. In this case, though, our side slopes are going to be greater. We're going to be 4 feet instead of 2 feet. So our minimum basal length is going to be 48.5 feet. And when we do the calculations for our width, it's the 625 divided by our minimum basal length of 48.5, and we end up with just under 13. We'll round up to 13. You can see it doesn't change the width all that much and the length all that much, but you do need to compensate for that and show that you want it installed this way. Now there may be a concern because we have so much sand of the stability of the side slopes. So what we're suggesting is that we add a side slope stabilization value. And what we're going to do is multiply that side slope by a factor of 2 and then add that to our basal length. So in this case we had a minimum side slope of 4 feet. So we're going to multiply that times 2. So we're going to add an additional 8 feet to our overall length, which is going to be really 4 feet on either end. So we're going to go from 48.5 to 56.5 feet on our overall basal length. And I'm suggesting that we stay with the same width. So our overall for this particular dimension or design was going to be 56.5 feet long and 13.5 feet wide. So here we're using very similar templates. We're going to be using again the slope site, showing the coils up the upper area. We're going to have our overall length and our width, and we should be good to go. Now the last thing we want to show on our submissions when we turn it into the local health departments is what the minimum required square footage will be, and we know it's 625 based upon our previous calculations. But it's also appropriate that we show what we're really going to have when we're left when it's actually installed, so that everybody knows what we're talking about here. So on our flat side, if you recall, we had 46.5 feet long by 13.5 wide, and that actually is going to yield us 627 square feet. On our sloping site of 20%, we're going to end up with quite a bit more of 734 square feet. And I would go ahead and show this to demonstrate that you actually have at least the minimum requirement that is required by the code. Now there's another factor that in our standard package we can't dictate or control or predict, and that is going to be what the length of supply line to the Oscar between the tank and the Oscars are, or the elevation difference. So this total dynamic head requirement on that supply line does need to be calculated, and of course each site's going to be slightly different. So what we do in our design manual, we have table 1 and also table 3 gives us an indication, actually table 1, table 2 gives us an indication of what I'm calling my excess total dynamic head is for each of the design flows. Now these are very conservative numbers of 50 feet, and this is how much TDH that we can have available to be used on our supply line. Let me show you what I mean. This is a fictitious pump curve with a fictitious operating point, but let's just say we're at roughly 13 and a half gallons a minute at about 80 feet ahead. With this particular pump, we would have this operating point, but we would have this excess head available to us for the supply line. So in our calculations, we're saying that this is 50 feet given the pump that we're specifying in our package. So to figure the total dynamic head, we're going to use friction loss and elevation between the elevation difference is going to be between the liquid level in the pump tank and the soil level where the Oscars are located. You can use the Hazen-Williams formula or tables to figure out the friction loss of that supply line, and then just use the elevation difference that you have from the site information. So we're also going to assume when calculating your friction loss that we're using 1-inch Schedule 40 PVC pipe. And again, we've got 50 feet of head to work with the pump that's in the package. If we determine that our TDH is more than 50 feet ahead, we're going to want to identify the system as a custom design and identify it. And I would suggest giving Low Ridge a call for assistance. We may do something as simple as changing the supply line diameter from 1.25 inches, or if it's a significant head loss difference and we need to actually specify a different pump and need to go to 230 volt, we'll also need to make sure that the control panel is changed to the higher voltage as well. So it's really important that if we vary from this 50 feet of head, that we identify exactly what that is so that it make it easier for the contractor to get what he needs from the supply house. And when you go out to do your final inspection, it'll actually do what it is that you anticipated happening. And again, this is just a reiteration of the same thing. The custom designs, again, if the TDH is greater than 50 feet ahead, or if your design flows are above 500 gallons a day. And this 500 gallons a day is really on the regulatory flow rate, not on the basal or the Oscar calculated design flow rate at 1.5, what the regulation has. So there's a little bit of a nuance there. In any event, you can always call and email us when you have a custom design or question whether you do or not. Be happy to help you with that. Now our tankage, again, the standards are 500 gallon a day tanks, 1,000 gallon for the septic tank, 1,000 gallon for the pump chamber. Both the vessels, they do need to be on the Idaho list of containment vessels. Again, a minimum of 1,000 gallons. Same thing with the discharge tank. If you have design flows that exceed the 500 gallons a day, the tanks must be upsized proportionately. You have to go up to a 1,500, 1,200, whatever the case may be. Again, so we have the proportional amount of retention time and storage volume in our tanks. Now, kind of want to take a look at the drawings that we have available, the standard drawings. On our website, this is our homepage. Oops, excuse me. It's our homepage. And what you'll want to do is click on the Our Products page. And what that do is you're going to have a choice of a couple of states. We have approvals in the 2 states now. What you'll want to do is scroll down and choose Idaho. And what that'll do is it'll give you the options of the various products that are available in Idaho, as well as all their documentation. And then what you'll find is a list of drawings. At the very top, you'll see that we've got not only tanks, but all the Oscar drawings are in CAD or DWG format. The rest of these are all PDFs, and you'll see that the OS300, the 7-foot coil sloping site, and so forth. So when you click on these and open it up, we'll go on the 300 gallon a day with the 5-foot coils. The page will open up, and you can download these and store them on your own computer if you wish. But here we have a 300 gallon design flow, which has 6 coils. It'll have the coils shifted to the upper edge of the basal area, and then the cross section shows exactly the same thing. So all you'll have to do here is just add the dimensions for your basal length, basal width, and then if you're different than 20% slope, you'll need to add what that value is here, and make that change. But these same templates can be used over and over again. The drawings nomenclature, they're all labeled OS dash, in this case 250, with a 5 or another value, and then an alphabetical number or an alphabetical character. The OS stands for Oscar Coils. The 3-digit number is the design flow, and this, again, the design flow after you've multiplied the regulatory design flow by 1.5. The 5 stands for 5 foot, and the S stands for a sloping site. So if you had a designation of a 7 with no S, it would be a 7-foot coil on a flat site. When the system is complete, the only cover that's required, here I've got listed C33 sand, but it's actually medium sand. Now you can cover the sand with some soil. We want to have it very low organics, and we don't want to have too thick of a layer. You might want to cover the sand with straw, get some grass seed planted or some other ground cover. If it's a real steep site, you've got a lot of extra sand, you may want to put some jute mat. That'd be fine too. What we don't want to do is to put a topsoil mix that you get from the commercial establishments that have a lot of compost, heavy organic material. That material tends to hold water, and it gets a little mushy, and it looks like your system's failed when it hasn't. So we discourage the use of commercial topsoil mixes. Just use mineral soil, and really the best thing is just to leave the top, just the sand itself. I'm going to talk a little bit about training procedures. With designers, we've gone through this class so far. We'd also like to be available for design review. So if you've done a markup on a design, we're happy to have you send that to us. We'll review that and give you comments. Happy to do that. If we just have general questions, call, email, text. That's just fine. With installers, we have a similar training type video we like people to go through. Once they've done that, then we have training, what we call with the first installation, where once the tanks are installed, we'll come out and show them how to actually do the plumbing for the Oscars, the setup of the headworks and the floats and so forth. Very simple, probably take about 20 minutes or half hour. And then we also come back after the system has been wired and do the startup procedures. We want to make sure that the wiring is done correctly, and hydraulically everything works well. We don't have any kinks or fittings that have been glued properly. And we're wanting the startup to be done prior to the final inspection, not as part of the final inspection. For the operation and maintenance folks, we go through the very similar process as we do with the installers. With the installers and the O&M providers, once they have gone through the class training and they contact us, we go ahead and put their name on our certified list of professionals, which we have posted on our website as well. This list is renewed annually, so we'll have to make sure everybody's up to speed with the latest and the greatest things that we have available. And then we'll also do some infield follow-up operation and maintenance procedures with the O&M folks as well. The website will be listed as certified professionals, and we'll have that also broken up into a couple different states. Washington, Idaho, obviously we're not going to have everybody on the same list. What we do on the list, though, you may not be able to read it too well. We do list the individual by last name, not the business, but the individual that's doing the actual either installation or operation and maintenance. Last name alphabetically, then first name, phone number. We also include the county that the business is located in, just for a point of reference for geographic purposes. And then we either make a check whether they're operation and maintenance or installer. In some cases, they'll be both. And to give a little indication of what an Oscar actually looks like once it's been installed, this system has been in for about one growing season. This is middle of the summer, and this is in the wintertime. I do have to admit this is Western Washington, so in your area you may have quite a bit of snow on top of here. But in any event, just by having sand over the top, we get a tremendous amount of lush vegetation growth, and people are actually using riding mowers on these. I recommend to use just a push mower, but they do get pretty solid footing after a season or two of growth. And this is a system that's just been installed. This was early mid-May a couple years ago. The property owner called me in quite concerned because he thought that there was a problem with the system because it was moist on top. You can very easily identify where the coils are. So it's important that the coils are placed symmetrically, because how you install them is kind of how the growth patterns of the grass may look, at least immediately after it, but hopefully not long term. But in any event, the grass, or excuse me, the wetting patterns are going to be very evident when you first put the system into operation. And this was 3 months later. Tremendous grass growth. The sand, even in the areas where it's still a little dry, it's still firm. They use just a push mower to mow this lawn, and when you walk on it, you can't tell that you're on a sand bed at all. Hope this has been helpful. Please email us, give us a call with any questions you may have. Appreciate you taking your time to learn more about designing Oscar 2s. Thanks so much.